Hello everybody. Yesterday I think we stopped at this point, file system consistency. We said that whatever we do, the bugs and mechanical drive failures and other unwanted situations can happen, and our file system could become inconsistent. What do we mean by inconsistent? There are many tables in our file system, and these tables might include information that conflict with each other. So from time to time, if we do file checks, system checks, file system checks, we are going to see these inconsistencies, and we should do these from time to time. Maybe every time you boot up your system, you should do the file system consistency checks, etc. If you found out there is a consistency in your file system, there should be ways of handling these consistencies logically, in a rational way, of course. That doesn't mean that you can always prevent any data loss, but doing something logical is better than doing nothing or ignoring the problem. That's what we talked about last time, and we had a simple file system consistency check algorithm that tries to make it consistent between the free blocks and the blocks in used tables in any file system. Do you have any questions about this file system consistency? I guess no. Then I will continue. Okay. Other thing is that we talked about this actually. We said that our hard drives are becoming more and more powerful in terms of storage space and also in terms of their capabilities to hold cache data. It is not unheard of to have gigabytes of cache space for a hard drive. I don't know. I mean, if you look at the specifications of 4 TB HDD, let's see what we get, what kind of okay. So if you go there for terabyte hard drives, how much cache spaces they have. So this is 1500 Turkish liras, and I'm wondering that myself too. Where is, yeah, this one? Do I have? Do you see it? Yeah, here it is. So 256 cache space, megabytes. It's not gigabyte, but megabytes, right? So that's a loss of cache space actually, and in fact, on my computer, the size of my SSD is this much, and that's it. Okay, that's all I have. I don't have any other hard drive. I don't have any other secondary storage space. All I have is 256. Okay, and no, this is megabytes, right? Not gigabytes. Do we have any other memories? No, that's it. So, well, it is not as much as I saw. Maybe this model doesn't have that much. HDD with, let me do it. HDD with large cache. Well, these are in the orders of megabytes actually. In the orders of megabytes. It's not even gigabytes. Anyway, that's a loss of memory, and you keep that kind of memory. So when you read, most of the time you read from the cache because of the locality principle, as you know. Okay, but we need to have a way of managing this cache. Okay, we call this block cache or buffer cache, block cache or buffer cache, and usually we try to implement the best algorithm that we can have. Least recently used. Remember, do you remember what we said about least recently used algorithm for the page replacement? Least recently used algorithm for the page replacement. We liked it so much. We said that it's a good algorithm, but there was a problem with it. Do you remember the problem?
Is it space problem? Because it uses 1 byte to keep least recently used or one.
Yeah, well, it is not exactly, that's the problem, but it is not the
It
space
never
problem.
forgets. It never forgets.
No, 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 it's not. What did the least recently use? It whenever you reference the page, it marks that page with a timestamp, right? Whenever you reference the page, it marks that page with a timestamp, so you know which page is least recently used, right? That's what it did. So we like this idea. This was good because every time I make a memory reference, I mark its page, so I know the last time I referenced it, so I can figure out the least recently used. But we said that this is problematic. This is good. The idea is good, but there is a serious problem with this one. What is the problem?
We need additional hardware.
We need additional hardware in the memory
To mark.
management unit to make this marking, right? Because every time I make a memory reference, I cannot do this in software. I cannot do this by operating system. That would take lots of time. I cannot execute an instruction I make a memory reference, right? So that would make all my memory references 10 times, 20 times slower. So maybe the memory management unit should do this marking by hardware, but that's expensive and we don't have those kind of memory management units. So we unfortunately we had to give up on this idea of least recently used. But when it comes to caching for our secondary storage units, this is not a problem anymore. Why? Why this is not a problem anymore?
Because I/O device is already too slow.
Yeah, every time exactly. I mean, every time I make a hard drive reference or the secondary storage reference, we are talking about thousands of times, thousands of times slower than the memory references we are talking about, right? So just spending a few instructions to keep a timestamp on a block memory hard disk block is not a problem. So I can spare that time. We are not we are not marking our memory references. We are marking our block references, and loading a block is infinitely slower than making a memory reference. So LRU can be implemented properly, no problem. So we are going to use LRU. Okay, so what does that mean? Every block, every block that is accessed, okay, in our cache will be marked by a timestamp, and I know which block was recently used and which block is least recently used. Okay, so I am going to replace the least recently used block in my cache. Okay, in my cache. So that's a good idea. So use the LRU. LRU is close to optimal replacement algorithm, as we remember. Of course, it is not optimal, but it's close to optimal because we are replacing the least recently used one. Okay, And we can do additional optimization on this LRU. Why? Because, for example, the inode. When you open a file, right? You load the inode block, I know that one, and read the inode block. And for a long time, I don't go back to the inode block anymore because I read all the data. But I know that I need to read that inode data or write it back to that inode data when I close my file. So even though I am not using that inode data, inode block for a long time, it is possible that it is very likely that it is almost certain that I am going to refer to it. So I know this one. Okay. So even though inode data, inode blocks are not most recently used blocks, I like to keep them in my cache. Okay, in my cache, so I can do this kind of optimization. And sometimes I can do just the opposite. I would say that inodes are so important. If there is a system crash, and if I lose the inode data, the whole file will be corrupted. That's too dangerous. So I am not going to keep this inode in my cache. Okay, inodes will be always in the inodes will be always in the hard disk. I am not going to keep it in the cache. So that block is essential to the consistency of the file system. So that might be another strategy. So we don't implement LRU as it is. We make slight modifications depending on the system. These two things are just saying just the opposite. Okay. One of them saying that inodes are important for the efficiency, so keep them in your memory, keep them in your cache. You are going to refer to it. The other one says that inodes are, they are going to be used later, but they are too important to keep in the cache. Okay. If you have modifications to inode, just write it to the disk immediately. Don't keep it in the cache. Okay. So depending on your system, depending on your design philosophy, you could do this. Usually the Unix systems work this way. Okay, they try to keep this kind of stuff in your cache. Windows systems work this way. So this is Windows, this is Unix. Okay, that's why in a Unix system, if you connect your USB drive to a USB port, okay, you mount it, you write some stuff to it. If you dismount it, if you unmount your USB disk and you just take your stick out, you will lose data because all the inode information will be in your memory and you didn't write them to your USB stick, and you are going to lose information. Windows doesn't do that. Windows always keeps modified data on the SSD drive or on the USB disk all the time. Okay, they say that this kind of information too important to keep in the cache. Unix doesn't say that. Unix says that, okay, I am going to keep them in the cache or in my memory. Okay, so if we are going to use the LRU, I am going to keep a queue linked list, okay, double linked list that keeps this least recently used page at the top, most recently used page at the bottom or at the other end of the queue, and it's a linked list. So I keep this linked list. So if let's say if I have accessed this one in the last secondary storage access, then I would put this at the beginning of this one because this one becomes the most recently used. Okay, so by modifying this linked list, every time I make a hard disk reference, by modifying the list links, I can do proper least recently used and most recently used assignments. But how do I make access to this one? I mean, how do I know that which block is which? I keep an hash table. This hash table, okay, this hash table says that that all the blocks, for example, very simple hash table maybe, all the blocks that belong to the block number between 1 and 100 is here. 100 and 200 is here, 200 to 300 is here, etc. Very simple hash table. I mean, it doesn't have to be this simple, but that's what I do. Okay, so using the block numbers, I can access any page that I like. This is all in the memory, and whenever I make a reference, I change these links, so I keep the least recently used, most recently used data. So by doing this again, I am doing this in the memory. This is loss of time, if you may think, but compared to disk access, this is very fast. Compared to disk access, this is very fast. This is thousands of times faster than going to the disk and loading this data, etc. Okay, any questions? Any questions? I think we talked about this already. And with the file system performance, we said that Windows has this philosophy of always keeping modified blocks on the disk. This is called write-through cache. Okay, this is called write-through cache. And in fact, if you remember it, I don't know, maybe I should load it. I think in the Intel TLB structure, I guess it was in the Intel TLB structure, there was a bit for the pages that it should be write through or not. And I think in that instance, I didn't talk much about it. Let me try to see if I can find it. This is Intel stuff. This is okay, segmentation stuff. Do you see any write-through bits anywhere? Write-through? Maybe it was in the Multics. Yeah, I couldn't find it, sorry. I think there was some place, there was a bit for a page. That page is a write-through page. Write-through page means that if I am modifying that page, I am immediately writing that page to the memory. I am not keeping, okay, or hard disk, sorry. I am not keeping that page in my memory if it is modified. So Windows is doing that. Okay, Windows as default, you can change this parameter, of course. Windows keeps all the modified disk blocks on the disk. It doesn't keep them in the system cache. Okay, it doesn't keep them in the system cache. So it is a little bit slow to modify files in Windows, but it is safer. In Unix, it is not that way. Okay, if you remove a USB disk from Unix system without doing a sync or without unmounting it, okay, will always result in lost data if you modify something on that disk. Okay, so I think you have all experienced this one. You lose your data because Unix keeps all the data in the cache, hard disk cache, secondary storage cache, if it is modified or not modified, and it writes them back when it needs the memory, or it writes them back when you sync your hard drive with the system, or when you do the unmounting. Okay, good. So you know this. Do you know how to change this behavior in Windows? I think they made it available. For a USB drive, you can say that I don't want this write-through caches. I want regular cache. If it is modified or not modified, always keep them in the memory. Do you know how to do that? How to disable write-through caches in Windows? how to disable write through. Write through cache in Windows. It looks like, okay, Windows 10. Okay, how to enable write caching. Okay, there is a, okay, expand disk. Policies. Switch to Policies tab and tick the enable write caching. So there is a way of doing it. So try this and try to see if it makes things faster for you. Yeah. Enable write caching on the device. So this is available. You need to be administrator and you can do that. Do this experiment to make it possible to keep all the modified pages in your memory, and try to write some pages to the hard disk and read them back, and see if it is making stuff faster for you. Okay. Do you understand the experiment, right? Since nobody is making any noise, I assume that you understand it. Okay, another optimization for the file system performance is the read ahead. As we said, if somebody is reading the beginning of the file, that means what? That person is going to read the rest of the file, right? Okay, if I'm reading the first block of the file, okay, the operating system makes an assumption that very soon block number k plus 1 will be read. So why don't I read it while I am at the same track? Okay, so even though nobody's asking for the block number k plus 1 yet, operating system reads it and puts it in the cache. When somebody asks that page in the next system call, that page is already ready in the system cache, and you can read it from the cache automatically. So this is called read ahead. So this works most of the time. Sometimes it doesn't work, so you end up wasting some memory space, and you end up wasting a little bit of system time, but that's okay, because most of the time it's going to happen. Okay, and of course this only works for sequential file reads. Okay, if you are doing random reads from block number k, then block number m, then block number l, and they are all unrelated, it doesn't work, of course. But if you are going to read it in a sequential way, this idea works. And the nice thing is this: since these are your tracks, okay, if this is your block number k, if this is block number k, your block number k plus will be here. So while your read-write head is reading this part of the disk, and your disk is spinning that way, after you read block number k, you are going to immediately see block number k plus 1 just next to it. So reading it doesn't take much time, because you don't have to do the seek again, and you don't have to wait for the rotational delay, because your read-write head is on at the k plus 1. So this is efficient. So the only thing is that you may need to replace a page from your cache, and if that page is needed later, that would make things a little bit less efficient. But other than that, it's okay. Okay, good.
Sir,
Yes.
but does it make it slower to take the page we wanted, actually? Not the k plus 1, but the k itself?
Well,
Because we are taking more,
yeah,
more required.
no, that's a good concern. But the thing is, I mean, as soon as you read the k, block number k, it is already ready and it can be used, okay? And the disk is busy, is going to be busy to read k plus 1. But I mean, as I said, it doesn't need any more head movements. I mean, the disk is already spinning, so I will not have any mechanical latencies, okay? I mean, what does the disk do if you don't ask anything? It is spinning anyway, right? It is spinning 700, 7,200 rotations per minute. It is spinning that way, and there is always some data available under the head. Okay, it doesn't cost you anything to read the data under your head. And while disk is doing this, and the controller is controlling this, your CPU can do other stuff. Okay. Of course, you are right. I mean, the reading k plus 1 is not free, because after you read the k plus 1, you have to buffer it, you have to make a new interrupt, and you have to stop your CPU and etc. But overall, if you are doing this in a sequential way, then this is the way to go. And they run simulations on this, and it works. Okay, good. This cache management is always tricky, and you cannot have 100% cache hit rates. There will be some misses. Okay, there will be some misses. You cannot avoid that. Good. Another idea for the disk optimization is related to reducing disk arm motion. Okay, depending on your file system, you can do lots of optimizations. What do I mean by this? For example, what do we do when we open a file in Unix? Okay, we have to go to directory. You load you find out the files inode. Okay, you load the inode. After you load the inode, you know the blocks of that file, and you go to the blocks and you read the blocks one by one. So it always starts with reading the inode, then reading the blocks. So it makes sense to keep the inodes and the blocks close to each other on your desk, so that you don't have to move your head, read write head a lot. You don't have to make a, for example, seek, or if you are going to do a seek, if you are going to do that seek operation, maybe the seek time should be very, very small, just a one track length of seek operation. So how do we achieve this? For Linux systems, they did this. They said that, okay, I am going to put the inodes in the middle of the desk. Okay, if this is my desk, if I keep my inodes in the middle section of the desk, whenever I open a file, I will go to this middle section of the desk. Okay, this middle section of the desk is the closest to, on the average, closest to all the other tracks. I read my inode. Then after reading my inode, I can go at most half the maximum seek times. Okay, so that's one idea. So I am keeping my inode. So after I load my inode, the most I am going to go is maybe towards the outer tracks of the desk or inner tracks of the desk, but at most I can go half of the maximum seek range, and on the average it's going to be the maximum seek range over 4. Okay, that will be the average. So that's an optimization. Okay, or some people do this. They say that, why do we keep inodes in the same track? I am going to divide my inodes into several portions. Okay, these are my inodes. The blocks that are specified by inodes are kept here. Okay, So the inodes and the blocks are very close to each other. Another set of inodes are placed here. The ones that are specified by the blocks that are specified by the inodes are here. Okay, so I don't have to keep my inodes. Okay, I don't have to keep my inodes in the same track. I divide them. Okay, they are called cylinder groups. Cylinder groups. Okay, so I have 1, 2, 3, 1, 2, 3, 4 cylinder groups in this case, and each group has their own inodes and their blocks, and that way when I read my inode, my blocks are very close. Okay, my blocks are very close. So this kind of optimization can be done with the Linux file system, Unix file systems. For the FAT-based file systems, you could do other kinds of optimizations. For example, keeping the FAT table in your memory. That's one thing. But as you remember, that takes lots of disk space, etc. Of course, these all are related to mechanical hard drives. With the SSDs, you don't have any mechanical. You don't have any mechanical parts. You don't have anything that moves around. So it doesn't matter where you keep your inodes, doesn't matter where you keep your blocks. Any place in your SSD will have the same access cost, will have the same access times. Doesn't matter because these are not mechanical. Okay, so what does that mean? Should we ignore all these kind of details when we write a file system for an SSD or when we write the drivers for an SSD? No, SSDs have other features, other properties, other problems. For example, this SSDs have this weird property that if you keep writing to the same position all the time, that memory position, that storage position becomes worn out and it doesn't work anymore. Okay, you cannot write to the same position more than 1,000 times maybe. Okay, you have this kind of weird problems with the SSDs. Not all of them, but some of them. So if you have this problem, what are you gonna do? You have to keep moving your inodes around because inodes are important. Okay, and you load them and you write to the inodes all the time. And inodes are system resources. You release them, you use them again. So they are important and they are frequently used. But if you keep your inodes in the same SSD location, that location will go bad, will die, and your SSD will get smaller. It may happen, but you may end up losing your inode, which is the most important, some of the most important data on your secondary storage. So SSDs have their own problems, their own advantages, their own problems, and you have to be careful when you are dealing with the SSDs. Okay, so that means what? That means depending on your secondary storage type, you may have your own optimizations, you may have your own problems to deal with. Okay, good. Okay, so at the end of this chapter, the book talks about the file systems of the popular operating systems, MS-DOS file system, the FAT-based file system. Okay, this is the directory entry for an MS-DOS file system. If you have a directory in MS-DOS file, original MS-DOS, okay, earlier versions of MS-DOS, each directory entry is fixed, and this is the total size. So total size is like 12, 22, 28, 32, 32 bytes. 32 bytes for each file in a directory. So in your directory, if you have 10 files, okay, this is the size of the directory file. Remember, each directory is a file, And what is the size of that directory? It is this many bytes if there are 10 files in it. At the beginning, you have the file name of 8 characters and 3 letters of extensions, so total of 11 characters, and that's it. Nothing more and nothing less. Because if you remember, the original MS-DOS file system can keep only fixed length file names, no exceptions. And then you have your attributes. What kind of attributes do we have for the MS-DOS file system? For the original file system, there is no ownership because it's not a multi-user operating system, right? You don't say the owner is this and that, and no, you can't. Okay, the attributes are usually: is this a system file? Is this a hidden file? Is this an I don't remember if there is an execution file or not. Let's say if there is an executable file. Yeah, read-only file. So each bit, so there is a 1 byte of attribute information. Then they said that we don't know what kind of features we are going to support in the future. So let's keep this 10 bytes for ourselves. And in the next release of this file system, maybe we could use some of them. So let's leave this space empty. Maybe they are using it, but they are not telling everybody. So this is the documentation. This is the official documentation of MS-DOS directory entry. Okay. So you can figure out for what kind of purpose they are using this 10 bytes. And as a system programmer, you may decide to use some of those bytes. But in the next release of this operating system, you may see that those 10 bytes are not used for that purpose anymore. So they are not making any promises. Then your time, date, stuff, and your first block number. So question, if this is your first block number, where is your second block number? Third block number? Fourth block number? It only tells you the first block number. Remember the Inode structure? Inode structure is like this. Okay. So in the Inode you have the attributes, and this is your first block, second block, third block, fourth block, etc. If this is not enough, then you have your additional block addresses and etc. This is Inode structure. With the fetch structure, you have only the first block number.
Maybe using the size information to figure out the second one.
But size says that I have this file is 722 bytes long, or 722, okay, 1000 bytes long. That's it. That's the size. 4 bytes. So you can have at most 2 to the power 32 bytes size files. That's it. So what does that make? 4 megabyte files at most. That's it. 4 megabytes is the largest that you can represent with an MS-DOS file system. Each block is maybe 4 kilobytes. So if you just have a single block, this should be enough. But where do I get that information for the second block, third block, fourth block?
Maybe they can be contiguous, so we can reach them as an array.
No, each directory entry is just 32 bytes of space. That's it. Nothing less, nothing more.
Attributes doesn't say anything about it, so
Attributes?
yes.
Attributes are system, hidden, execution, read only, etc. And just single byte, just 8 bits. How can you say? I mean, if each file is 4 kilobytes, that means that 2 to the power 12, right? 2 to the power 12 each block. And if I can have 2 to the power 32 bytes, that means that I should be able to assign 2 to the power 20 blocks for a single file at most. So there should be 1 million, more than 1 million blocks represented for a single file. But only I am saying single block. Where is the rest of the blocks for this file? If it is sequential, then I can do that. Maybe that's a good idea. It is sequential. Okay, you give the first block number, then you know the size, so you can calculate all the blocks. But I mean, as you know, on our hard drives, that kind of thing doesn't happen. For CDs, yeah, but for hard drives, it doesn't happen. Where are the rest of these blocks? Come on, people. I've been talking about this maybe 5 times. This is the most important difference between Inode structures, Inode-based file systems, and what is FAT? What is file access table? What is FAT?
An old file system used in embedded systems.
Well, well, it is used in embedded systems, yeah, for nowadays. But what is it? I'm trying to go back to the definition of FAT file system. Where is my indexes? Okay, file types. Yeah. Okay. So that was it. Okay. How do you implement the files? It is either linked list allocation. Remember this one. Once you get the first block address, okay, physical block number 4, there is a linked list, and this linked list says that, okay, this is my first block, and in this block there is a linked list section. It points to the next block and next block and next block. It goes that way. So there is a linked list representation. But what did we say about this? We said that making a traverse on this linked list is expensive, because every time I make a block access, I have to go to that disk position and get it, and next one, next one, next one. Sequential access becomes so slow. Random access becomes so slow. What are we gonna do?
Amcaya söyle ama. Amcaya söyle önce. Amcana söyle bak dediğini.
Eve. 5 dakikaya geri gel, tamam mı? Ben ders yapıyorum şimdi.
Söyle.
Yiğit Efe. Şimdi ders yapıyorum Sevil Hanım. Biraz sonra bir 5 dakikaya gelin ya.
Hoca dersini bitirsin sonra
So this is a linked list structure, and we didn't like it that way. What did we do? We kept our linked list in the memory like that. Okay. So there is a linked list structure, and it keeps the linked list like that. And when you say file A starts at block number 4, then I can follow this link. 7, go to 7. 2, go to 2. 10, go to 10. 12, go to 12, and this is the end. Okay. So this is called file access table, FAT structure. Okay. That's called the FAT. So this is how you do it. That's the idea of FAT. And I kept talking about this. I don't know why you guys are not giving me the answer. So that's what that is. Okay. The first block number, and the rest is obtained from the FAT, file access table, linked list structure. Okay, is it clear now? Say yes.
Yes, sir.
Okay, out of 106 people, 2 people said yes. Okay. And the FAT system that we talked about, we don't know the block sizes. Of course, the block sizes are not in the directory entries because it's a system-wide parameter. And with FAT12, FAT16. So how about this one? What is 12? What is 16? And what is 32? And I'm going to give you a hint. What kind of a FAT system directory entry is this? Is this FAT16, FAT12, or FAT32? 12.
Number of blocks.
Explain that a little bit, Doruk.
Because when I count to bits, 32 bits, sorry, byte.
So what kind of FAT system does this directory entry belong to? Is this a directory entry for a 12 FAT or 16 FAT or 32 FAT?
32.
How did you get that?
I added byte.
Oh, you are saying that this is 32 byte thing. No, it is not. No, no, no. Definitely not. Definitely not. Look at this first block number. First block number is a 2 byte value, right? That means that I can address at most 2 to the 16 blocks, right? So that's the beginning address. So this is a FAT16 directory entry. For FAT12, okay, FAT12, you are going to have 12 bits. Out of these 2 bits, maybe they are going to use the 12 bits. But for FAT32, you will need at least 4 bytes to that information. Maybe later in later versions of FAT, maybe they had used some part of this reserved section to keep that information. I don't know. Okay. So what is the size of the size of the FAT, the file access table for a FAT16 file system? Of course, it is 2 to the power 16 elements has to be there. So it's a linked list of 2 to the power 16 nodes, and each one has 2 bytes in it. Good. Any questions on this? Okay, so it is this kind of file systems are adjustable when you first install your file system, first initialize your file system. You tell the system that each of your blocks are, for the FAT12, maybe half a kilobyte, 1 kilobyte, 2 kilobytes, or 4 kilobytes. For FAT12, these are options. For FAT32, you can have at most 2 megabyte or 2 gigabyte blocks. It is possible. And you can have at most 32 kilobyte blocks. If you have 32 kilobyte blocks, your file system, the total file system could include 2 gigabytes of data at most. With FAT32, 2 terabytes is the limit. Okay. So what do you do if you have a disk? Okay, let's say this is my disk. This is my disk as a linear space. This is my disk as a linear space, and I have let's say uh, 512 gigabytes of disk space. Okay, 512 gigabytes of disk space, but I am using FAT16 on this one. FAT16 means that at most I can have 2 gigabytes of space. That's it. So how can I keep all of this space useful with FAT16? Is FAT16 a bad idea for this kind of an hard drive? Because out of 512 gigabytes, I could use only 2 gigabytes of space. Is that a good idea? Maybe let's make it less dramatic. Let's make this like maybe 16 gigabytes of space. So this is 2 gigabytes space occupied by this FAT16 file system. So what's going to happen to the rest? I cannot address it, right? So what is your solution? What should we do? You might say, okay, let's switch to FAT32. I don't want to do that for some reason. So what would you do?
Maybe mapping, like we did in virtual memory, page table entries.
Don't invent anything. Just use a technique that we already know. It's a technique that you already know.
Invert table.
We never talked about inverted tables in secondary storage. At the beginning of this chapter, we talked about something. What was it? Partitions. Remember the partitions? I would partition this disk into 8 different file systems, and each file system is a FAT16 file system. Okay, so at the beginning of this disk I have the partition table, so I cannot address the whole disk as a single drive, but I have to make like the drive C, D, E, F, G, like that. Okay, for the Windows file system. Or for the Unix, if I am using the FAT16 again, under the directory mount, I have to mount all of them, all 8 of them. Okay, they have to be different directories. And their file systems are different. Okay, good. Okay, I think I need to take a break right now. Let me take a break. And during the break, please read the whole chapter and come back. Because I'm asking questions and nobody's answering me. What happened? You are not reading the book anymore? Or better yet, you are not listening to me anymore? We talked about all of them. Okay, 10 minutes of break. Be here around 12:35. Okay, I figured out where to find that write through cache switches. Okay, I inserted a new USB drive to my computer. This is my SSD disk. Okay, if I look at this one, here it says that cache write through policy. Okay, this one has a write through policy. No, it is disabled. So this is more efficient. So this writes to the cache, not directly to disk. But if I go to this USB disk, it says that that's the fast removal. That means that the write through is enabled. If I like to choose disable write through, then it says that this may cause some data loss. Okay, so I made this available for this disk. Now it is mounted and write through is disabled for this one. But unfortunately, I think I don't have. I think this is not formatted. It doesn't have. Okay, let me show you. Let me show you the possible file systems that I can put on this disk. Okay, here if I like to format it again, it will ask me, okay, what is the size of this one? It's like half a gig drive, and the file system is exFAT. What are the other stuff? NTFS FAT32, I think is the default. exFAT. Let me switch to NTFS, and now it is asking me the block size, and block sizes can change from half a kilobyte to 2 megabytes. I'm going to make it 2 megabytes and just format it. I think it is being formatted. It's going to take some time. Yeah, okay, it is done now. It is in NTFS, file system NTFS, and my block sizes are large, very, very large. So even a single byte of file for this drive D, okay, for this drive D is going to take lots of space, 2 megabytes of space, right? Maybe we could test it. Let's try to see if it really works. So this one, let's go to this. What is the size of disk? How do I, okay. So how much memory is free now? 418 megabytes is free, and I am going to make a simple file on it, just a simple file, new txt file. Okay, just test file. I did that, and let me put just 1, 2 in it and save it. Its size is very, very small, and you see it went from 418 to 416. So 2 megabytes of space just wasted for this 2-byte file, because the block size is 2 megabytes, right? I hope this makes sense. Does this make sense? Come on, people, are you listening?
What will be the disadvantage of making the block size really small instead of 2 megabytes?
So you tell me, Doruk, what is the disadvantage? I think I asked this question maybe 2 times or 3 times. Now you are asking me the same question. Good, okay. What would be the disadvantage of having such a small block size? So that was a trade-off, right?
The size gets bigger.
Say it again, Fatih.
The table size gets bigger because
Yeah,
we are
the
using
the fat
more
ta
tabs.
yeah, the fat table size gets bigger. Okay, let's try it. Okay, so if I don't have anything on this file system, let me remove it. I removed it, so this one became again 418. Is it? How do I? Okay, maybe do it. I think it was 418 megabytes was the free space for a brand new drive. Okay, so for some reason it uses 42 megabytes of space. That space is for the fat table on that disk, and I am going to format this disk again. Where is my disk? It is the disk is here, and let's format it. This time let's use very small size, and I am afraid that I am going to format my main drive. Okay, this is okay USB. Yeah. Okay, always be careful. So it is formatting and formatting, and it is done. Okay, let's go to the properties of that. Okay. So let's look at the properties. It says that the use space is 13, and this is 446 megabytes is available. This is even more space is available. I don't know what happened. So changing the block size made more memory available. I don't know. I mean, I don't know the details of how the NTFS. Oh, we are not. Sorry, I am sorry. We are not using. We are not using the FAT. We are using NTFS. NTFS is different. NTFS is using inode idea. It is using inode idea. Let me format this. Let me format this using our stupid.
32 because of less internal segmentation.
The drive is empty. There is no segment. There is no fragmentation. It is empty. Okay. So with FAT32, make it small and format it. 32 512, and how much space do I have now? I
Sir,
have.
you pressed kapat
You
instead
didn't.
of başla.
I did not format it.
No, you didn't.
No, you didn't.
Okay, let's go to the FAT32. FAT32 is kind of an advanced file system, but it is based on FAT, and I say do it and do it. So I have 452 available. Okay, let's format it again with FAT32 with 4 meg block size. Now I have 556. Okay, it is more. So there are 4 megabytes of difference, right? 4 megabytes of difference.
Don't see the other part.
Say it again, Mohammed.
How many megabytes is free space available? We don't see that right now.
I see it here. You see that?
Oh yeah, okay. Yeah, okay. I thought you were looking at the detail
Yeah, okay,
table.
yeah. So that's it. So I mean, making the block size smaller keeps some makes your fat larger. Okay, good. So instead of you, I am doing the experiment for some reason. I mean, you should be doing these kind of experiments, not me. Okay, good. So this is how the MS-DOS file system works. When we come to Unix, okay, let's compare this picture. This is the MS-DOS file system directory entry, and this is the Unix v7 file system directory entry. All you have is the file name, 14 bytes, okay, and the inode number. It is so simple. Why is it so simple? Why is it so simple?
Because MS-DOS doesn't have much functionalities.
But the simple one is the Unix, not MS-DOS.
Oh, okay.
I mean, this one doesn't have any attributes, right? I mean, who is the owner of this file? What are the protection flags? Is this executable? What is the last modification time? Where are those?
At the disk, yeah. Because we keep only small size of information for the file in memory.
So where are those attribute information?
I think it's at the disk. Keep in the disk.
Well, I know that it is at the disk. Where is it? It cannot be in the air, right? Yeah, it is on the desk. Where is it? Where is it on the desk?
Inode, I think, indicates this information.
You think it is inode, okay. Yeah, it is in the inode, and this is the structure already, okay. So this is the 7th time I am showing you the same picture. This is the inode. So for each file you have the inode. Inside the inode you have the attributes, all kind of information. Who is the owner, execution, the privileges, permissions, read-write permissions, modification dates, also the block numbers. And in this implementation, the block numbers are first direct block numbers. If they are not large enough, okay, if they are not sufficient, then I have the last one, the third one from the last one. I have a link to a single indirect block. So this is a block of indexes. Each one has an address of a block. Okay, let's say I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, direct blocks. And if each one is a 1 kilobyte block, that means that this inode itself can have 10 kilobytes of disk space or file size. If that is not important, then I would use this link. This link is going to show me another block, and inside this block I will have lots of block addresses. And if this is not enough, then I can use this second link, and the second link is not a single indirect block, it is double indirect block. So each address is a block of not data but block of other block addresses. Okay, so let's say each block can have 2 to the power 10 addresses. Okay, so 2 to the power 10 addresses will come here, and this one, each one can have 2 to the 10 addresses, but each one can have 2 to the 10. So each one is 2 to the 10. This one is 2 to the 10. That means that I can have with this block 2 to the power too many blocks. And if it is not that enough, then I have the triple indirect block structure. With this one I will have 2 to the 30 blocks, because each one can have 2 to the 20 and each one can have 2 to the 10. Okay, so Unix inode structure from Unix v7 file system works this way, and there is no centralized file access table. when you open a file, you load all that information to your memory. And you are not allowed to keep lots of files open in your memory. That's why you don't keep that much data in your memory related to files.
Sir, I want to ask something. I'm not sure if I understand it correctly. Let's, for the sake of simplicity, for the sake of giving an example, let's assume a flash drive with 4 gigabytes of block size, okay? And I just put a file which is 1 megabyte. Does it still take 4 gigabytes of space and I cannot put any other file?
Mohammed, the experiment that I did at the beginning of this lecture is exactly that one. Remember, I just create a file. I just created a file, just 2 bytes, and it occupied 2 megabytes of space on the disk because my block size was 2 megabyte.
Okay, now I see.
That was the experiment. And then Doruk asked me a question: what happens if I keep my block size small? Well, in that case, each file is going to have minimum of 12 bytes. Doesn't matter how many bytes you have in it. Okay, the smallest file is going to have 12 bytes of data on the disk, but your file access table is going to be larger.
Okay, I understood it correctly then. Thank you very much.
Okay, it is better for you to ask other. Okay, good. Okay, let's move on. And I think I showed you this before. And in the root directory of this v7, suppose I have this. I have only these. Okay, in the root directory I have these file names, and for each file name I have the inode numbers. Okay, and inode number for user directory is 6. If I go to inode number 6, okay, inode number 6, I see that all the properties, attributes for that directory. It says that I am a directory, this is my mode, this is my size, and these are my access times and creation times and etc. And then what? Okay, I store my files, I store my information at block number 132. Okay, so you go to block number 132, and inside the block number 132, you have all that file information. Since this file is a directory, I have directory entries in there. And next to each file name, there is an inode number. And in this case, by coincidence, all the file names are directory names. And if I go to this AST, inode number 26, I see that one. Okay. So this is the main inode structure of Unix systems. And TFS is using an idea like this. Okay, that's why, remember, when I use a smaller block size, the available space change a little bit differently because it is not using a FAT file system. FAT32 is not a pure FAT file system either. It uses ideas from the inodes because it's a newer file system. But FAT16 is the classical one. Okay, good. Any other questions? I think that's oh no, that's not it. Another file system is I think we talked about this. This is the CD-ROM file system. Okay, ISO 9660 file system. CD-ROMs, they use this file system because CD-ROMs are special. They are read-only drives, read-only secondary storage systems. What does that mean? There is no writing to it. If there is no writing to it, it doesn't make sense to have write true or no write true because you are not going to write it. You cannot have modified pages or modified blocks of a CD-ROM cache. Okay, that's a very good optimization. Also, since nobody is going to modify any data on the CD-ROM, when the CD-ROM is created, you can optimize all of your files so that they are stored in a sequential manner. because I know them, right? So there is no external fragmentation with the CD-ROMs. It cannot happen if you do it in a smart way. If you create your CD-ROMs in a smart way. So lots of optimization can be done with the CD-ROMs. And this file system ISO 9660 file system takes advantage of it. Okay, and the CD-ROMs initially they are developed for storing audio. Okay, for playing music, for playing audio. That's why the addressing in CD-ROM is done not by the block numbers but by minutes and seconds. You would say that I am going to put this block at 7-minute 30-second mark. Okay, it is easy to translate this into blocks because 1 second of data corresponds to 75 blocks of CD-ROM. So you can use the block addresses too. Okay, so let's go to this file system and let's look at the directory structure. Okay, this is the directory structure of CD-ROMs. At the beginning, 1 byte, you would say the length of this directory entry, 1 byte. So that means that it could be at most 256 bytes. Okay. And then there is another field that says that I can add more data to this. Maybe just a minute. No. Do it this way. Okay. So this is the length of the directory for this one, and there is this extended attribute record length. So there is this extension. I can add more data plus 256. So 512 bytes of data can be kept in the directory. So what do we have? This is the location of the file. What does that mean? Location of the file? The starting address of the file in terms of blocks or in terms of minutes, seconds. I don't know the details, but it is 8 bytes. 8 bytes is lots of data, so 2 to the power 64 blocks can be addressed. Lots of data. And the file size again 8 bytes. Lots of, and date and time. These are some flags. These are some storage related fields. In CDs, you can have multiple volumes. Okay, if you have a file that is larger than a CD, you can do it with the CD file system. And then we have the file system, file name again. Remember with the file name, again, it is limited, 4 to 15 characters. You cannot have anything larger, okay, with this case. And as you see, I'm going to ask you the same question again. This is the beginning of the file, the first block, okay? This is the first block address. Where is the next block on the CD-ROM?
Can you repeat the question?
Yes, I agree.
I am asking the same question that I asked before. What did I ask you before? I said that, okay, this is the first block number for this MS-DOS file system. Where is the next block? And I am asking the same question here. This is the, okay, address of the beginning of the file on the CD-ROM. Where is the next block? This is the first block address. Where is the next block?
The first block indicates the next one.
No.
No.
First block because it's sequential.
Yes, as I have repeated maybe 20 times, in CD-ROMs all the files are stored in a sequential manner. So it is enough for you to have just the beginning of the file and the size of the file. That's it. Everything is sequential in a CD-ROM. We have the luxury of having things in sequential. because there is no writing to it, there is no modification to it. Okay. It turns out that after they set this standard, it turns out that this information is not enough to make the CD-ROMs accepted everywhere, because if I am going to use a CD-ROM in my Unix file system, under a Unix file system, I need lots of more information, such as who is the owner, what are the execution permissions, read permissions, etc. Right? That kind of stuff. Where am I going to put them? So they put these extensions. So remember, there is this extension part, the padding part. I can add more information to it, and they specified new extension standards. This is called rock ridge extension. Okay, with the rock ridge extension, in that 256 bytes of this extension place, they keep the POSIX attributes, that is the Unix related attributes, and then the major and minor device numbers are related to Unix again. If there is a symbolic link, I have that information. Alternative name, what is alternative name? This name is too limited, it is at most 15 characters. I like to keep more data for the name, and the child location, parent location of that file for the directories. Okay, and sometimes sequential storage is not sufficient for some files, so they have to divide the file into more than one place, so they use this relocation data for that one, and timestamps. This is called rock ridge extensions for this kind of standard. And then that wasn't enough. Some other people introduced these extensions: longer file names, Unicode character set, like the characters for Turkish characters, like these, and this one, right? Turkish characters or other characters. And in CD-ROMs, first at the beginning, they made the restriction of having at most 8 levels of directories. 8 levels of directories. Okay, so it is possible to go deeper than 8 levels now. And directory names with extensions is possible with these extensions. Okay, so they say that although I am specifying this when they first introduced this standard, it is possible to extend this using this padding area. Okay, so we looked at 3 different file systems: FAT file system, MS-DOS file system, Inode file system, and this file system. So these are kind of the extreme ends of different ideas, and of course it is possible to have combinations of these ideas. NTFS is such a thing, EXFAT is such a thing. Okay, any questions about file systems? Okay, if there are no questions, I will start the new chapter. I am not liking how you guys are doing with the class. Nobody's asking any questions. I am asking the same question over and over again, maybe the 2-3 times, and I cannot get satisfactory answers from anybody. Okay, it's not going good. Okay, not going good. So, but I won't stop. I will continue with the new chapter. This chapter is about chapter number 5 and input and output. Okay, so with the input and output, let's stop and let's try to remember what we did first. In chapter number 1, it was the introduction. We talked about what an operating system is, what are the motivations for us to study the operating systems, the main tasks of the operating systems, the management of the resources, and the abstracting the details of the hardware. Right, those were the two things, and then we talked about the different types of operating systems and the hardware, etc. So the introduction chapter was like a very very brief operating system course. We talked about everything actually. Then in chapter number 2, we abstracted the CPU and we came up with the idea of processes and the threads. Okay, processes and the threads are the abstractions of the CPU. So as a regular programmer, I think that the CPU belongs to me, and I write my programs and I execute them. But in fact, I am sharing that CPU with many other processes, but I don't notice it. Okay, so those are the processes. What if I have to share some data with the other processes? Then that's called inter-process communication. Then we talked about that. And in chapter number 3, we said that let's abstract away the details of memory, because I have to share the memory with other processes. Memory is a very large place, but it is not large enough for me to keep all of my data in there. So as a programmer, I like to think in a simple terms. I like to think I have a very large memory space address. In fact, I don't, but it is the task of the operating system and the hardware to hide this information from me. I do my addressing like I have all the memory space, but everything, the address translation from virtual addresses to physical addresses, paging in and out, segmentation, all that kind of problems are handled by the operating system with the help of the hardware. That's what we did. And then we looked at the file system, the secondary storage. Okay, for me, a file is a permanent storage place where I can address it from the byte number 0 to some large byte number. I open such a file, I give it a name, I write data to it, I read from it, and that's it. But there are many details of this file creation, appending, updating, modifications, and etc. And those kind of details are handled by the operating system. Okay, and operating system is very careful about keeping the data safe and keeping it consistent. So those 3 things are very important. Okay, and as we said at the beginning of the chapter number 4, if you know these 3 things very well, okay, as an undergraduate student, you have almost sufficient information about the operating systems. Okay, you started understanding what an operating system is. Okay, so these 3 things are very important, but that doesn't mean that they are the whole story. There are many other things that you need to know, or at least it is better for you to know about the operating systems. And one of them is the input output. And this chapter we are going to look at this input output. Okay. Okay, we provided abstraction for processes, address spaces, and files. Okay, and operating systems, the computers have to deal with the input-output devices. Okay, so by input-output devices, what kind of things do? We send commands to input-output devices. We say, read me some data from the network, or write this data to the screen or to the printer, etc. We send commands to the devices. If the devices need to communicate with the computer, they create interrupts, and we catch those interrupts and we handle them. And this is not a beautiful world. There are many problems happening, and we have to handle those errors. These are the main tasks of the operating system in terms of handling the I/O. Okay, and I/O is complicated because you need to deal with the hardware details. Dealing with hardware is not easy. You have to know about the hardware. You have to know about the communication between the hardware, and you have to do this in an efficient way. Okay, so regular programmers, even the experienced ones, will have lots of difficulties if they try to handle the hardware, the I/O devices, by themselves. So they would ask operating systems help. Okay, for me as a regular programmer, opening a file is as simple as open function. But depending on where file lives, it could be a mechanical hard drive file, SSD storage file, network file, or CD-ROM file. Many things are happening differently, and I don't have to know about those changes, differences. Okay, all I like to do is just open the file and read my data. Okay, the operating system has to provide this abstraction for you, and that's what we are going to look at this one. Since there are many types of I/O devices available for computers, okay, there are very different kinds of code available for them, the drivers. Okay, and many of them are filled with details of how to deal with this, the hardware specification, hardware properties, hardware communication protocols, and etc. That's why the I/O code for an operating system, the amount of the number of lines for I/O devices is very, very large. Okay, the I/O code represents a significant fraction of the total operating system. Okay, total operating system, because these kind of things are very, very related, and there might be many things can go wrong. Okay, many things can go wrong, and we have to handle them. We have to handle them, and just be aware of this. The I/O part of the operating system is complicated in terms of the number of lines that they had to write. Okay, so principles of I/O hardware. We are going to look at some structure of the I/O hardware, but we will not go into very details because this is not a hardware course. We like to know about the I/O hardware necessary for us to write device drivers for them, or necessary for us to understand them. Okay, then we are going to look at the principles of I/O software, and then we are going to look at the individual I/O devices. Okay, so first a review of I/O hardware, then review of I/O software, then let's look at I/O devices one by one, including the hard drives and the SSDs and maybe CD-ROMs. Okay, so in the file system we looked at the software part of the file system. In the I/O we are going to look at more mechanical or electronic properties of I/O devices. I/O devices doesn't mean that we have the hard drives only or SSDs only. We are talking about the keyboards, we are talking about mice, cameras, network drivers, network cards, and etc. All kinds of I/O devices, anything that you connect to your computer. Okay. With the individual devices, we are going to look at them. Okay, so let's look at the types of the I/O devices. Basically, there are two main types of I/O devices. One of them is the block devices. The second one is the character devices. Block devices are, as the name implies, you communicate with these devices in terms of blocks. You would say, read me this block number, write to this block number, etc. Okay, so our hard drives, our SSDs, CD-ROMs, Blu-ray discs, USB sticks are common block drive devices. Okay, so you don't talk to these devices character by character or byte by byte. You talk them block by block, and the block size, as you have seen, is specified during the system installation or formatting of your device. Character devices, on the other hand, it's a stream. Okay, you read a stream or you write to a stream. It is not addressable. You don't say, give me this block number or give me this character number 7. You say that, okay, read me a character like from the keyboard. Okay, and keyboard gives you a character. That's it. You don't say that, give me the character number 15. Okay, no, you don't say it, because that's not available. You have to get all the characters before character numbers 15. Okay, like the mouse. Mouse is doing the same thing. It keeps you giving you X and Y addresses of the mouse icon, mouse pointer, Also, it gives you the button status of the left and right buttons or the middle button, whatever. Okay, so it is not addressable, does not have any seek operation. Okay, so we usually like to think about our I/O devices like this way, but this is not a very complete way of classifying devices, because there are some devices that doesn't fit into these categories, such as clocks. System clock. System clock is a very important peripheral I/O device because it is the one that causes the timer interrupts. Okay, without the timer interrupts, as you know, there is no preemption. Without the timer interrupts, we wouldn't write very efficient page replacement algorithms. Without the timer interrupts, some of the I/O devices wouldn't have any clue about are they stuck somewhere or are they doing good. Okay, so the clocks are important, but the task of a clock is you tell the clock that give me an interrupt in 5 seconds, and it gives you an interrupt in 5 seconds. It doesn't fit into this block devices or the character devices. It is not sequential, it is not block addressable, but it's some kind of a device. So some of the classes, some of the devices are not within these two categories, and we are going to spend more special time. We are going to spend more time on these kind of devices later, and we are going to talk about the software for these kind of devices.
Can I ask a question?
Sure.
Is block devices are use block spatial files? Can we say that?
Yeah, block devices are block spatial. Why do you think they are different?
I don't know.
No, well, yeah, they are the same thing. Block devices, block spatial devices are the same thing.
I mean block spatial files.
How block spatial files? What's a block spatial file?
We so that are used to from model disk.
Where did you hear it?
From book.
I don't
Block
remember.
spatial.
Well, I mean, we could we could map we could map our memory, or we could map character devices to special files. You remember that? Okay. You would say that I am opening this file. I am opening my keyboard as a file. So my file
Yes.
is connected to the keyboard. Whenever I read some data from the file, okay, I am reading it from the keyboard. In that case, my file is not block based, but it is character based. If it is a block special file, I guess that's the definition. That file is connected to a block device. File is an abstraction. File is an abstraction that I could use to access the block devices or the character devices. Okay, so files are not always um connected to block devices, hard disk or blue disks or that kind of stuff.
Okay, thank you.
Okay, so these are some of the examples for I/O devices. Some of them are very old, keyboard, mouse, and these are the speed data rates. Okay, so the fastest here is, we don't have USB 3.1 or 3.2. They are much faster than most of this stuff, but historically they were used. Okay, so this 56K modem, does anybody remember These modems, 56K modems, early days of internet. When you connect up to the internet, when
I
you
just heard it from my dad, and that's it.
yeah, so you heard from your dad, and that's it. Yeah, so these were the fastest. I think these are 56K. I think I have used 300 baud modems in 1993, maybe, yeah. 300 baud, so it is much slower than those. So what you're gonna all you can have is the terminal, like this terminal, and even that was a very big luxury for us. Okay, without leaving your home, you connected to your main server and you type your homework. That was revolutionary those days. So even this one, these were unheard of, very expensive modems, and our machines didn't support these anyway. They were not fast enough, so nobody remembers them. Nowadays we have very fast USB or Thunderbolt devices. They are very fast. Okay, I think I will stop here. Please read the chapter about file systems. We will keep going back to them. Also read this chapter too when you come back next week. We will talk about these devices, the hardware review, and we are going to talk about the software side of it. Okay? And do experimentation and ask me questions. Like experiment with file systems, experiment with system monitor on Windows and Unix and other operating systems, whatever they are. Okay, I'll see you next week.
Have a nice day, sir.
Bye.